Hi, I'm Lawrence Forsley, and with my colleague Teresa Benyo, I want to discuss our NIAC 23 project accessing icy worlds using lattice confinement fusion fast fission. An overview, introduction, mission context, robotic probe specifications and options, innovation, potential impact, and some takeaways. So introduction, I think everyone in this audience is familiar with the Ocean World Exploration Program and the Cryobot and the Tunnelbot from NASA Glenn, examples of robotic probes. Critical to us, since we're designing a power system, is the Cryobot reference that Hockman and others have put together, where power density should exceed 1 watt per cc. Total power needs to be between 8 and 12 kilowatts. It needs to have a 2 to 6 year operating lifetime, and sometime in the next 10 years it needs to be TRL-6 and flight ready. So the mission context, icy world exploration, the idea is to burrow through anywhere up to 40 kilometers of ice. We've suggested in some of our work a heated or ultrasonic drilling mechanism, and our thought is that a lattice confinement fusion fast fission can provide nuclear electric propulsion to get there faster and can provide the heat to get through the crust. So addressing some of the conditions of icy worlds, on the right-hand side, there is a chart of the multiple phases of ice. You'll notice ice 9, Kurt Vonnegut's favorite. It lives in a very small space here. Interestingly, today, PNAS, the National Academy of Sciences, published a paper on another form of ice from saltwater brine that may explain some of the things that we've seen with spacecraft going over these icy worlds. There are various ice phases. There's also likely to be subsurface ice lakes. And again, looking at the robotic probe specifications and options, our main point here is to understand what the volume, the mass, what the power requirement is, and the lifetime as well. And in our case, the innovation is what we call lattice confinement fusion technology. And the need is to develop, in our view, a non-fissile, compact, scalable nuclear source. It's possible it could also produce a high ISP nuclear electric propulsion. And future development could go beyond this to being a lightweight power source for other missions of planetary power. Lattice confinement fusion works by having very high density fuel, as shown over the side, with a lattice of atoms. And one of the ways that this works is we have a neutron come in, hits a cold deuteron, heats it up, induces a fusion reaction. This is also dependent upon electron screening and the very high fuel density. For example, tokamaks have a fuel density of 10 to the 14 ions per cc, whereas in solid matter you approach 10 to the 23 ions per cc. And electron screening can increase the fusion rate anywhere from 10 to 20 orders of magnitude. Now, by taking the fast neutrons from this, we can essentially take a lattice of an actinide, uranium or thorium, and then in turn fission that. So we get the best of both worlds. We get a fusion-driven fission reactor, hence the hybrid. So the potential impact is we can use this for probes for icy moons. We don't require enormous amounts of 238 plutonium. We believe we can produce a small low-mass variable power output. And the hybrid approach does not need HEU. And another possibility is that we can use both the reactor thermal waste and we can potentially use electric power to vibrate our way through the ice shelf. So the takeaways are it's a hybrid fusion fast fission power system. Again, no HEU or HALEU required. We recognize that icy worlds are going to require an enormous amount of flexibility between changes in ice phase temperature and pressure changes. And by combining both ice melting and perhaps acoustic penetration, we can take advantage of the skin layer adjacent to the probe. And in closing, I'd like to thank the Cryobot workshop organizers for inviting us. And both Teresa and I look forward to learning more from you as the changing requirements. And we look forward to increasing the TRL of our LCF fast fission.